Good day to you. This is teacher LELAND Alejandro, and we're going to do exponential functions before we take on the domain and range for exponential functions. Let us try to see our basic examples using the desmos.com. Okay, so let me provide one exponential function equation. All right, this is y equals 2 raised to x, and see how it looks like there. Okay, you can see it from the screen. You can see it from the screen. This is what you call the exponential growth. Okay, exponential growth. So you see from a lower value to an increasing value of x. Okay, you can see the curve. It goes to a very, very high value. Okay, as you increase the x gradually, it goes to a rapid increase there, exponential growth. Okay, now this happens when your base is higher than 1. Okay, higher than 1. So you see our base here is 2. Okay, you can see the equation here. The base is 2. And you see the graph, the nature of the graph. As you increase x, it gets to a higher value, very, very high value. Now let's have another one. Say we make our base 3 raised to the power x there. So you can see the blue graph here. The nature is also increasing as you increase your x here, like that. So this is exponential growth, okay? Exponential growth. Now, we can actually translate this by adding some numbers or by subtracting some numbers. So, but still the nature is exponential growth. So let me show that translation. So say, for example, 2 to the x, and then we're going to add something, say plus 3 there. Still, the nature of the graph is increasing, okay? But it's slightly elevated from 0, okay? It went up to 3 here, okay? Still, the nature is, as you increase your x, the value of the function increases rapidly, okay? There. You can also change the level of the graph by subtraction. We can have here 3 raised to the power x. Say we subtract, say 1 there. So you can see the violet or the purple graph, the nature is still increasing, but the level moved to -1. All right, now let's study how to determine domain and range, okay? Domain and range, just by looking at the graph. We shall start from the first example. Okay, going back to the red graph, this is y equals positive 2 raised to x, okay, and the nature is exponential growth. You can see the nature of the graph. This is flat, almost flat line at y equal to 0 here. The x-axis is equal to the name y equal to 0. So this particular x-axis is actually y equal to 0. And I can show you that by typing y equal to 0 there. Okay, y is equal to 0. That's the x-axis. All right, this y equal to 0 is the asymptote. Okay, that is the line approached by the red graph. As you make x more negative, okay, here, as if they were touching. This graph red and this graph that is colored black, okay, looks like they're touching, but actually they are not, okay? This is only the line approached by the red graph as you make the value of x more and more negative to the left. So no matter how far to the left you make x more negative, it will never touch the graph. It's asymptotic, okay? Now, the straight line, the black line, is what you call the asymptote. And you actually spell it. All right, it's supposed to be like this. There. It's the line approached by the graph, but never touching it, okay? It will never intersect with it, okay? And that is the y equal to 0. You call that the asymptote line. All right. Now, let's go back to domain and range. Okay, the domain for this exponential function, okay, the domain you can see is the set of all real numbers. That means there's no restriction for x. You can go as far as left, you can use the value as far as left, and you can also use the value as far as you go to the right, positive values. So there's no restriction. You can just imagine that if you make your x very, very positive, the value of the function is very, very high. And you can see the inclination of the red graph, it's not vertical, it's diagonal. So that means if you increase your x to the right, it will meet, but at a very, very, very high value, exponential value. So you see the domain is the allowable value of x, and we can write it down. So domain set of all real numbers. Yeah, that will be for the domain for this function, okay, exponential function. How about the range? How about the range? Okay, the range is the value of y, and you can see it clearly. Okay, you can see it clearly from the graph. Okay, and the y values cannot reach 0. As you make your x more negative, it will only approach the value 0. And then as you increase your x, okay, for positive values of x, your y is going to be very, very high. So that means the limiting value is 0, and it cannot be equal to 0 as you make your x more negative. Remember, it's only approached by the graph, but never touching the y equal to 0. So the range, if we're going to write the range for this exponential graph, okay, y is greater than 0, okay? There is no or equal, okay, because it will never be equal to 0, okay, for the value of y. So this will be the range, and this will be the domain for this particular example. Now, let's try to change the base, okay? Let's try to change the base for another example. Let us, let's make this 3. Say, for example, y is equal to 3 raised to the power x. There. We just simply change the base, but still is higher than 1. It's 3, positive 3. There. You can also make it, say, decimal. Say y is equal to 3.5, okay, raised to the power x. There. It's not always integer. For as long as it's higher than 1, okay, it will be exponential growth, okay, exponential growth. Say 4.7 raised to the power x, there. So still the numbers we're using is higher than 1, okay. So this will be the nature of the graph. Now let's go back to our first example, the 3 to the x. Okay, going back to this graph, all right. Now, you can see the nature of the graph. We still have the domain, the allowable values of x is from negative infinity to positive infinity. And you can see the nature of this graph. This is not vertical. This is diagonal. That means for a very positive value of x, this will be a very, very high positive y. Okay, you can imagine it going to the moon. Okay, so that will be a positive value. So this will now be something which will have a domain, which is all values of x. So still our domain for this particular example, y equal to 3 to the x, the domain, that will be a set of all real numbers. There. Set of all real numbers. And of course, how about the range? How about the range? Okay, you can see it from the graph. Okay, you can see it from the graph here that it can never reach y equal to 0. So that means it's greater than 0 or higher as you go up. Okay, so you can see it. It will be a very, very positive value, and the minimum is just higher than 0. Okay, all right. So the range is y supposed to be greater than 0. So take note, we don't use the greater or equal because it cannot be equal to 0. It's supposed to be higher than 0. The range is supposed to be higher than 0. There. All right, let's try another example. Exponential growth. Okay. Say, for example, we use the same example here, only we will add some translation. Say we add 1 there. Okay. All right. If you have something like this, the domain will still be the set of all real numbers from negative infinity to positive infinity, but the range will slightly change. So our domain here is the set of all real numbers there. And the range, of course, is different. Okay. You can imagine making your x here from the equation. If you make this 3 to the negative, say 1000, 3 to the negative 1000, that will be almost 0. Okay, that will be almost 0. It will approach the value 0. Plus 1, then it's 1. It approaches the value 1 also. So the approach value here, okay, the approach value here is 1. So the limiting value of y, and then all values of y upward. So our range is y and higher than 1. There. That will be the range. This will be the range. And your asymptote here, the line approached by your graph, as you test the end behavior to the left, okay, as you check the end behavior of your red graph, okay, you can even check it out. See there, it's approaching the line y equals 1. So where is this y equals 1? We can type it here, y equals 1 there. That's your asymptote, the line approached by the graph there. Okay, but never touching it. Okay, never touching it. So your range is y must be higher than 1. So it's 1.001, 1.002, 1.003, and then 2, 3, 4, 5, 6. Yeah, those are the allowable values for y. That's the range for this particular exponential equation. And this is exponential growth. You can see it goes up. It goes to a high value as you increase your x. This is what you call the exponential growth. Now let's go to the exponential decay. Okay, exponential decay starts from a very, very high value and it goes down. Okay, and this happens when you have a base which is in between 0 and 1. In between 0 and 1. And this is how it looks like. Y is equal to, say, 1/2 as the base. 1/2 is in between. 1/2 is in between 0 and 1. Okay, and then we will raise this to a power, say, the variable x there. And observe the graph. Okay, it starts from a very, very high value, and then as you increase your x from negative to positive, it approaches the value 0. So if you make this x, say, 1000, then that is almost 0. Okay, that is almost 0. 0.5 raised to 1000. All right, your calculator will give 0. Okay, but in reality, that it will not. It will not become 0. It will still have some positive y value. So this graph approaches y equal to 0 as you increase your x, but never becoming 0. Okay, so you can see this graph. This is what you call the exponential decay. Okay, so instead of increasing, this one decreases. Okay, decreases as you increase your input x. Okay, so this is what you call the exponential decay, and we can have several examples. Just selecting the value of the base in between 0 and 1, say 3/4 raise the power x there. Okay, you can see, you can check on the red graph. It starts with a high value and it goes down there as you increase your x there. Okay, you call this exponential decay. Okay, all right. Now we can actually determine the domain and range for this. Okay, the domain and range for this. Let's remove the second. All right, and concentrate on the first graph. Okay, all right. You can see the allowable values of x. Okay, we can have it from negative infinity to positive infinity. Remember, you can see this graph here. This is not vertical. This is diagonal. So there is a corresponding value for y, no matter how more negative your x will be. Okay, so there is a corresponding value of y because this is diagonal. Okay, so that means if you set your x more negative, this will have a very, very high positive value. So the domain is from negative infinity to positive infinity. That's the domain. And we can just say the set of all real numbers. There, the set of all real numbers. And of course, we can determine the range, okay, just by looking at the graph, okay. By looking at the graph, you can see you can never reach 0, only some positive value close to 0, say 0.001, 0.002, like that. So we can say the range is from value higher than 0. That will be for the range. Okay, so we shall type the range. Okay, it's y higher than 0. Okay, so check on the symbol. It's only greater, not greater or equal. It's greater. Okay, so you should be able to differentiate that. Okay, this means greater. Let me emphasize that. That's greater. Okay, greater. This one is greater or equal. Greater or equal. Okay, and the second option is not true. Okay, because the graph will never touch y equal to 0. Remember, it will only approach 0, but never touching it. Okay, as you increase your x here, as you increase your x here, okay, this graph, this exponential curve will only approach the line, which is the x-axis, but it will never touch it. So the range is y greater than 0. Okay, it's this one, this. Okay, all right. So this you have to erase. Okay, it's this symbol here, this symbol here. All right, so that will be for exponential decay. Okay, now let's add some translation. Okay, so say for example we have something like this. If the graph is like this, say y is equal to 1/2 raised to the power x, say plus 1 there. Okay, let's examine the range. The range is now changed. Okay, the range is now looks like from value just higher than 1. Okay, higher than 1 because the asymptotic line is y is equal to 1. The line approached by the graph is y equal to 1. This line here. Okay, so the domain will still be the same. Domain will be the set of all real numbers. So this will be the domain, set of all real numbers. There, the set of all real numbers. And of course, the range is now changed. Okay, because of this one here, if you analyze this, if you make your x more and more positive, it will approach zero. It will approach zero. Okay, that means this term here will have a very, very, very small value. Okay, approaching zero. And then if you add one, then it's a value which is slightly higher than one. Okay, that means it approaches the value one. Okay, and so this is going to be only y higher than one. That will be the range. Y is greater than one. That will be the range of the y value. And that will be it for our examples. I hope you were able to learn how to determine domain and range for exponential equations or exponential functions. And that will be all for our discussion for this. We're going to have the logarithmic next time. All right, so see you later. Bye-bye.